Hello there, welcome to Lecture 30, Light Emission. From the lights we use in our homes, to the lights illuminating our smartphone screens, to the sun in the sky, light emission is a very big part of our lives. This video will explore different types of light emission processes, from incandescence to lasers. Each of the following concepts will be discussed in this video: light emission, incandescence, fluorescence, phosphorescence, fluorescent lights, light-emitting diodes, and lasers. As discussed in Lecture 11, electrons exist around the nucleus of an atom. They travel like waves in orbitals, and these orbitals are characterized by the amount of energy of each electron. Each atom has unique energy levels that each electron can have. The lowest energy level is known as the ground state, and then there are excited states that represent more energy. We can model those different energy levels using an energy level diagram. Electrons can only reside in one of the energy levels of an atom and cannot have an energy that is in between levels. Energy levels are therefore known as discrete. They only take on certain quantities. An analogy would be the potential energy of a human in a building. Let's say you can move between floors only by jumping, no stairs and no elevator. In that way, you can only have potential energy values that are given by the height of the floor that you're on. You can't be between floors, only on one floor or another. Electrons can move between energy levels. When an electron gains just the right amount of energy, it can jump up one or more levels. Electrons can gain energy from being excited by light waves or by collisions with other electrons or subatomic particles. Eventually, electrons that are in an excited state will decay back to the ground state. During this process, the electron will emit light. The energy of that light will be proportional to the frequency of the emitted light, and is equal to the difference in energy between the two energy levels that the electron jumped between. The equation we can use to determine that frequency is E equals hf. The energy of light is equal to Planck's constant times the frequency of the light. Planck's constant, represented by a symbol of the lowercase letter h, is equal to 6.6 times 10 to the negative 34 joule seconds. Each atom, with its unique configuration of energy levels, has a unique spectrum of light that can be emitted during electron decay. It's possible for electrons to decay between any two levels, meaning that many different frequencies of light can be generated. An atom with 4 energy levels, 1 ground state, and 3 excited states, represents 6 possible transitions and 6 different frequencies of emitted light. It's possible to determine the composition of stars by examining the frequencies of light they emit. These frequencies can be compared to known emission spectra of different gases, such as hydrogen and helium, to determine the exact elements that are present in stars and other celestial bodies. The spectra of gas discharge lamps can be measured with a diffraction grating. These images show the different spectral lines of light emitted in this manner. Before LED lighting was ubiquitous, many stores would use neon lights in their signs. These neon lights could contain neon, a noble gas that emits an orange color, or other gases that emit different colors as well. Sodium vapor lights were commonly used on highways, as they are a relatively efficient way to generate high-intensity lighting, perfect for driving at night. Sodium vapor lights can be identified by their unique yellow hue. Many of these lamps are being replaced by LEDs, which are capable of generating a more pleasant white color. While an emission spectrum showcases the light emitted by a material, an absorption spectrum shows the wavelengths of light that are absorbed by a material. If white light is shined upon a sample, the sample will absorb particular frequencies given by its energy level diagram. Those frequencies will be subtracted out from the white light and appear as black lines in the absorption spectrum. Incandescence is a form of light emission previously discussed in Lecture 16 in the context of heat transfer. All objects emit electromagnetic radiation with a frequency that corresponds to the temperature of that object. Relatively cool objects, such as humans, plants, and animals, emit light in the infrared portion of the electromagnetic spectrum. Hotter objects will emit light with higher frequencies. At a high enough temperature, objects will emit visible light. In this manner, we can use the color of an incandescent object to determine its temperature. An incandescent object that appears red or orange is cooler than an incandescent object that appears white or blue. Incandescent light bulbs use the property of incandescence to generate white light. A very thin filament is heated by passing electric current through it. This heat causes the filament to incandesce with multiple overlapping wavelengths of visible light. The mixture of all visible light creates white light, as discussed in Lecture 27. Using a diffraction grating, we can see a continuous rainbow spectrum emanating from an incandescent light bulb. Today, we use incandescent bulbs less and less in our homes and work environments, as the process of incandescence to generate light is very inefficient. The power consumed by incandescent light bulbs is quite high compared to LED and fluorescent lights, as discussed in Lecture 23. Much of the electrical energy we use to light an incandescent bulb is wasted as heat. In this demo, I use a hand crank generator to light up different bulbs. First, I crank the generator to light up an incandescent bulb. This takes rather a lot of energy to do, and the bulb lights only dimly. Then I turn the crank to light the LED bulb. This bulb lights right away. It is very easy to illuminate. An LED bulb requires much less energy to function. However, note that the LED only illuminates every half cycle in an AC generator. This problem can be fixed in home lighting by converting AC to DC, as we discussed in Lecture 23. Other examples of incandescence in our daily lives are seen in electric stoves and toasters. Both of these objects contain resistive heating elements. Electric current is sent through the heating elements, which then warm up due to their resistance. At cool temperatures, they will glow red. As they warm up, they will glow orange, or possibly even yellow if very hot. When the electric stove or toaster is turned off, both still emit light via incandescence. Since we can't see it, the light is not visible. As the objects are likely at room temperature, we can expect that light to be in the infrared region of the electromagnetic spectrum. Fluorescence is a process of light emission where an object absorbs light at a high frequency and then during the electron decay process emits light at a lower frequency. During this process, a minor amount of heat is generated, which is what causes that change in frequency between the absorbed and emitted light. Energy is conserved. Fluorescence has many applications in the medical field. A fluorescent dye can be attached to certain types of cells or other biological materials. When excited with a high-frequency light, the fluorescent dye will emit light at a different frequency. This is particularly useful because the high-frequency light is usually bright enough to overwhelm any other light. By filtering out that high-frequency light, only the fluorescent light can be collected, allowing scientists and doctors to see only the parts of samples that are attached to the fluorescent dye. They emit at a different frequency and would not be blocked by that filtering process. In this manner, particular types of cells can be imaged, biological processes can be viewed, and the presence or volume of cancer or bacteria can be measured. Fluorescence is also present in nature. Some types of animals and fish exhibit fluorescence. Even plants contain a fluorescent molecule, chlorophyll. Some minerals and rocks are fluorescent as well. We can see these colorful fluorescent emissions when shining a UV light on the minerals. Phosphorescence is a light emission phenomenon similar to fluorescence. Similarly to fluorescence, a phosphorescent material will become excited by high-frequency light and re-emit lower-frequency light. However, in phosphorescence, This process of re-emission is extended for a time period even after the exciting source is removed. Sometimes it is a few seconds, sometimes it can be several minutes. Many glow-in-the-dark paints are phosphorescent. When illuminated during the day with sunlight or room lighting, the electrons in the material gain energy. At night, after the illumination is removed, the glow-in-the-dark paint will slowly re-emit the lower frequency light over the span of several minutes or even hours. Chemicals known as phosphors may emit light using the process of fluorescence, and some may emit light using the process of phosphorescence. Phosphor coatings are very common when high-energy light is used to generate white light. By mixing multiple phosphorescent or fluorescent chemicals together, a mixture of red, green, and blue light can be generated to create white light for use in home lighting. Fluorescent lights use the properties of light emission and phosphorescence to generate light. A mercury vapor inside of a glass tube is excited into a plasma by applying a high voltage to it. Mercury plasma emits light in the UV region of the electromagnetic spectrum. On its own, this UV light would be useful for sterilization or other medical uses, but would not be a good light source for our homes due to the presence of ionizing radiation. The surface of a fluorescent light tube is coated with a phosphor. This phosphor absorbs the high-energy UV light and generates other colors of light. The exact chemicals used in the phosphor coating depend on the color temperature of the light. So-called cool lights emit more blue wavelengths, and so-called warm lights emit more yellow wavelengths. When you go to the hardware store to purchase fluorescent bulbs, you will see different color temperatures available depending on the lighting effect that you prefer. Because the mercury vapor emits light at discrete frequencies, and the phosphor coating also emits light at certain frequencies, although the phosphor emission has a broader spectrum, when using a diffraction grating to look at the spectrum of a fluorescent bulb, the combination of both of these effects can be seen. Each of the lines of the mercury vapor emission spectra can be seen, with some blurring between those lines due to the broad phosphor emission spectrum. Light-emitting diodes, or LEDs, use two layers of semiconducting material stacked together to create current flow when a voltage is applied in a certain direction. A semiconductor, as described in Lecture 22, acts somewhere between a conductor and an insulator. A diode, which we discussed in Lecture 23, acts like a one-way valve that only allows current to flow in one direction if voltage is applied in the correct orientation. When current flows through the two layers of semiconductor, at the junction between the two layers, electrons flown from low to high voltage and holes, the absence of electrons, which are a feature of certain types of semiconductors, flown from high to low voltage, will combine and create light. Every light-emitting diode will generate light at a particular frequency given by the exact semiconductor that's used to create it. Engineers and scientists have created LEDs that can generate frequencies from UV to infrared. Light-emitting diodes are monochromatic. While their spectrum may encompass a small range of frequencies, they are not capable of generating a broad range of frequencies. However, LED lighting in our homes is very common. How is this possible? There are two primary methods for generating white light with light-emitting diodes. The first is to package three separate LEDs together, one red, one green, and one blue. This is known as an RGB LED. By combining red, green, and blue light together, using the color addition process described in Lecture 27, white light can be generated. RGB LEDs are used in tunable light bulbs. The second method for generating white light is similar to that used in fluorescent bulbs. A UV LED is packaged in a piece of epoxy that is coated with a phosphor. Depending on the exact phosphorescent chemicals used, different color temperatures of white LED bulbs are achieved. Photovoltaic panels, or solar panels, function by the reverse process. Light that's absorbed by a semiconducting material will release an electron-hole pair, generating electric current. This is an excellent method of creating energy that does not require fossil fuels and uses a process totally different from the generators we discussed in Lecture 25. The term laser is an acronym for light amplification by stimulated emission of radiation. A laser contains a light source to start the process. A laser pointer will likely contain a light-emitting diode as a light source. This light source shines into an amplifying medium. This can be a gas or even a solid material that amplifies light by means of stimulated emission. While this is a very complicated process, in general, it means that the material is capable of generating more light from the initial light source. In addition to the amplifying material, a laser contains two mirrors, one on each end, to cause the light waves to travel back and forth throughout the material. This does two things. First, it causes the light to spend more time in the amplifying material, creating more light by stimulated emission. Second, it causes the light waves to interfere, creating light waves that are all in the same phase and have the same wavelength, using the process of constructive interference. The output of a laser contains light waves that are very high intensity and also completely identical. This type of light is known as coherent light. Coherent light means that all of the waves have the same frequency and phase. These properties of laser light make them extremely useful in many scientific and industrial applications, from laser welding to laser surgery to laser printing and everything in between. Thanks for taking the time to learn about light emission. Until next time, stay well.